Today we're going to talk about our fifth test for determining the convergence or divergence of series, and that is the integral test. I'll start by telling you exactly what it says. The integral test says that suppose f is a continuous positive decreasing function for all x greater than or equal to a, and also suppose that b sub n equals f sub n. Then, if the integral from a to infinity of f of x with respect to x and the sum from a to infinity of b sub n, if we look at those quantities, the integral and the sum, either both converge or both diverge. This is probably really confusing to read right now, but I think it'll make more sense when we look at this first example. So let's start with an example that we already know whether it converges or diverges. If we look at 1 over n squared, we already know this converges by the p-series test. Now, however, we're going to prove it by the integral test. What the integral test says is that we need to turn the terms of our sum into a function, which really just means that we're going to take 1 over n squared and turn it into the continuous function 1 over x squared. What we need to check next is if this function is continuous. Immediately a red flag should go off. 1 over x squared is definitely not continuous for all numbers. It's discontinuous at 0. But we're only looking between 1 and infinity. So between 1 and infinity doesn't include 0, and it is continuous on the values that we're looking at. So it's continuous. It's always positive. 1 over x squared, because x squared is always positive, it always stays above the x-axis. And it's decreasing. As we plug bigger numbers in for x, my overall value of f of x gets smaller and smaller because of that x squared in the denominator. So once we determine this is an acceptable function, what the integral test says is that if I look at not the sum from 1 to infinity, but the integral from 1 to infinity of 1 over x squared with respect to x, what it says is if this integral converges, then the series is also going to converge. And the good thing is that we already know how to evaluate this improper integral from last week. We're going to look at the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. All we have to do now is anti-differentiate. We get negative 1 over x evaluated at b and 1, which means we substitute b in for x, subtract off substituting 1 in for x. As b goes to infinity, that term goes to 0, and we see the integral converges to 1. What the integral test says is that because the integral from 1 to infinity of 1 over x squared dx converges, then we know that the sum from n equals 1 to infinity of 1 over n squared also converges. And so we've proved the convergence of this series using the integral test.